Right, so these are conservation of energy sample problems. So now that we understand all of our energy and we understand all of the ideas of conservation, our goal is to apply them to these problems. So they are not the same. I'm only going to show you some samples, and then you should be able to apply it to any situation because they're always going to be a little bit different. So let's start with number 1. A roller coaster is pulled to the top of a 12-meter tall hill. What is its speed when it reaches ground level, assuming no friction? So no friction means there's no outside net work. Remember, gravity doesn't count because we have potential energy. So we'll draw a picture just to figure out what kinds of energy there are. So we've got a roller coaster, and it's sitting down here, and then it's getting pulled up to here. And it's going to go back down like this, so it's going to end up down here. So we did some work to bring it up there, but it doesn't ask us anything about that. We know that it's 12 meters high when it gets here, and we know that it's at 0 meters and it's moving at some speed when it gets here. So the first thing I have to ask myself is at the top at position number 1, and this is position number 2. At position number 1, what kind of energy does it have? Well, type of energy it has is GPE. And when it gets to the bottom, what kind of energy does it have? KE. So I know that my GPE is equal to my KE because the other one's at 0 at the end. So in my given, I'm going to have H equals 12 meters. Notice that's all it gives me. It's like, what the heck? That's it. The unknown is what is its speed? So that's going to be V. And my equation is going to be GPE. Technically, it's change equals KE. Technically, it's with a triangle, but because one's 0, it just becomes the one is equal to the other. And so as I'm solving it, I end up with MGH equals 1/2 mv squared. So then I can say, okay, I can cancel out the m's on both sides. I'm trying to find v, so I'm going to multiply both sides by 2 to get rid of the 1/2, and then I'm going to take the square root to get rid of the square. So what do I end up with? I end up with v is equal to the square root of 2gh. And then I can just plug it in. So when I plug it in, I end up with the square root of 2 times 10 meters per second squared times h, which was 12 meters. So then that's 20 times 12. Take the square root. Don't forget your square root. Common. People forget to take their square root. 15.5. Look at your units. So you notice that the units, if I look here, it's going to be meters squared per second squared, but there's a square root. So I take the square root of that, so then I can say, oh, that's meters per second. All right, problem number 1 done. Try problem number 2. What is the minimum energy needed at ground level so a 200 kilogram roller coaster can successfully complete, there's an extra D, but that's okay, complete a loop-de-loop that is 8 meters high. All right, so let's draw a loop-de-loop. And we have a roller coaster, and it's going to go around like that, and we know that the height of this is 8 meters, and we know this is 200 kilograms. So we know it's going to have kinetic energy down here, right, because it's moving, and the GPE is 0 down here, right, because it's at the bottom. And we know it just has GPE up here, and that the kinetic energy is 0 down here. So just like the last time, we're going to end up with kinetic energy is equal to gravitational potential energy when it gets to the top. The difference is it told me the amount of, I'm trying to find the energy, not the velocity. So again, they're always just a little different. So in my given, we're going to have m is equal to 200 kilograms, and H is equal to 8 meters, and our unknown is energy. In this case, it's going to be kinetic energy because that's the only energy it has. But I'm going to leave kinetic energy as KE because I don't need to know anything except for the energy is equal to, and now normally you'd say kinetic energy is equal to 1/2 mv squared, but not in this case. Because remember, we said the kinetic energy is equal to the potential energy, and we know potential energy is equal to mgh. So now I can say kinetic energy equal to mgh. So when I solve it, I simply have KE in this situation. So you can't, this is not an always. This is, in this particular situation, the kinetic energy gets transferred into GPE. And now I can just plug it in. So KE equals 200 times 10. It's a 10. That is a terrible 10. Let's make it better. 10. And then times H, which is 8 meters, times 8 meters. So that means I do 200 times 10 times 8. I plug in my calculator. I get 16,000. I look at the units and I see kilograms, meters squared per second squared. I see kinetic energy, and I know that is joules. Done. Problem 2. So they're really not hard, but you do have to think as you do each one. Let's try number 3. A 0.5 kilogram pendulum moves at 12 meters per second at the bottom of its swing. What is its GPE at the top of its swing? Okay, so here's my pendulum, and it's going to swing like that, and we know it's moving at 12 meters per second here. We know at the bottom that GPE equals 0, so it only has kinetic energy at the bottom. And at the top, we know that KE is equal to 0, so we know it only has gravitational potential energy at the top. That's all I know. Oh, and I know the mass is 0.5 kilograms. Right? So am I given M equals 0.5 kilograms and V equals 12 meters per second? My unknown is GPE. And again, in this one, we'd say, oh, well, GPE equals mgh. But I don't have H, I have V. But I do know that is equal to the kinetic energy at the bottom. So I can simply say GPE equals KE equals 1/2 mv squared. So now, for this one, I have GPE equal to 1/2 mv squared, and then I can simply plug it in. So it's 1/2 times 0.5 kilograms times 12 meters per second squared. If I plug that in, I get 36. So this is equal to 36. And again, kilograms, meters squared, second squared, GPE. This is equal to my GPE. And so that's equal to joules. Okay. Halfway. Let's go to the next. So now, number 4, a girl runs off a dock with 20 joules of kinetic energy onto a boat. The boat was at rest. If all of the girl's energy is transferred to the girl boat system, how far will the boat travel, assuming the water resistance is 2 newtons? All right, water, dock, boat, girl. All right, so the girl is running, and then she ends up in the boat, and then they move off together, right? But it's going to stop, right? It's going to stop over here. So my V is going to be 0. So that means my KE is going to be 0 when it's done, and my GPE is equal to 0. What? Where'd all the energy go? Well, let's see. She started off, she was moving with 20 joules. So she had KE. And we're assuming, it doesn't say anything about height, so we're just going to assume they're all at the same level. So the GPE was 0 here. But what happened? We had a force over a distance, right? And we know that F times D is equal to work. So all the energy was lost due to the work of the resistance of the water. So in this case, we start with KE and we end up with work. So in my given, I'm going to end up with KE equals 20 joules, and F is equal to 2 newtons. My unknown this time is D. So I know that my kinetic energy is going to be the same as the work done on the boat to make it stop, which is equal to F times D. So when I solve it, KE equals FD. I do have to solve this for, what am I looking for? Distance, right? So I got to solve it for distance. I'm going to divide both sides by force. So what do I end up with? I end up with, oh, I don't want to write that yet. I end up with D, different color. D is equal to KE over F. So now my solution is D is equal to 20 joules over 2 newtons. Oh, easy math. 10. Right? That does not look like a D, does it? Oh, funny looking D. D is equal to 20, or equal to 10. 10 what? Let's see, a joule, remember, is a Newton meter, and divided by a Newton, so that cancels, so we're left with meters. So it's equal to 10 meters, which makes sense because it was distance. See, the math is easy. It's just figuring this out first. Oh, heat engine. A heat engine does 20 joules of work to lift a piston with a load while expelling 5 joules of heat to its cold reservoir. What is the heat energy transferred from the hot reservoir? We don't really need to draw a picture because it's already hard enough to draw a heat engine, so I think we can just go with the words. So 20 joules of work. So work equals 20 joules. And cold reservoir, heat is Q, cold reservoir is equal to 5 joules. And our unknown this time is the hot reservoir, so heat, Q, hot, H equals question mark. And our equation for this one, you may or may not remember, is that QH is the energy that goes in, and out comes work and QC. So that's already solved. Cool. So super simple math again. QH is equal to 20 plus 5. So that's equal to 25 joules. To J. Cool. Last one. A college student needs to lift her 25-kilogram suitcase into a van that is 2.5 meters above the ground. They are only able to lift 200 newtons. How long of a ramp will the student need to get the suitcase into the van? Okay, do not judge my grammar. It's not a good sentence, but we got the idea. So let's draw a picture for this one. So here's a ramp, and we've got, what is it, a suitcase that we're trying to get into this van that's up here, right? So the person has to push, right, with some force this distance, right? So we're going to call that F1 and D1 because that's what I'm doing. That's what I'm putting in. And then I have to lift it up against gravity. So I have to lift it up against gravity. Oh, FG. How do I find FG? Oh, yeah, 25. So it's 25 times. See how that keeps coming back? It's 250 newtons. So I'm going to lift this against gravity. I have to lift 250 newtons. but I can only push with 200 newtons, right? And it says the height of van to that is 2.5 meters. So this is 2.5 meters, which would be D2, right? And this would be F2, because that's what I need the machine to do for me. It's going to lift it up. All right. So in my given, F1 with me, 200 newtons. That's all I can push. And F2 is the 25 kilograms, but changed into newtons. So that's 250 newtons. And D2, that's how high I'm going to lift it, is 2.5 meters. So it's important that you make sure the ones and the twos all match. That's why I wanted to draw the picture. The unknown is how long of a ramp. So D1. And we know the work in F1, D1, work is equal to the work out, F2, D2. Now I can just solve for D1. So I divide both sides by F1. That's simple. Now let's move this up. So we end up with D1 is equal to F2 D2 over F1. Plug it in. D1 is equal to 250 newtons times 2.5 meters, all divided by F1, which was 200 newtons. Right. Notice the units. This really is ratios. If you look at it, it's the ratio of the forces to the ratio of the distances. But I notice the newtons cancel, and I'm left with meters. So D1 is equal to 250 times 2.5 divided by 200, which is 3.1, and I'm left with meters. And it should make sense that I need my ramp to be longer than the height because I wanted to be able to push less than I had to lift. That's it.